Hi everyone, my name is Mike Byrne and I'm a lecturer at the University of St Andrews and a Marie Curie Research Fellow at the University of Oxford. So today I'm going to be talking about amplified warming of extreme temperatures over tropical land. So I'm going to try and understand why the warming of the hottest days over land in the tropics is considerably faster than the warming of the average day. And to do this, I'll start off by showing some results from model projections of future climate, and then I'll spend the majority of this talk developing a new theory to understand this amplified warming of extremes in the tropics. Okay, so we've known for quite some time that the hottest days over land are expected to warm more than the average day. So here's a figure from a paper in 2016 by Sonia Seneviratne and others, showing in two particular locations, so on the left in the Mediterranean and on the right in the contiguous USA, the warming of the hottest day per year in simulations of future climate on the y-axis versus the global mean temperature change on the x-axis. And the black dashed lines in each panel are the one-to-one lines. So what we see is that the hottest day each year in this location is warming considerably faster than the global mean temperature. So these blue and red lines and the shading, the slope of those lines are much steeper than the slope of the black dash line. So this is indicating that at least in these two locations, models are suggesting that in the future, the hottest days per year in those locations will warm considerably faster than the average day. Looking in particular at the tropics, here I'm showing the temperature change for the hottest 5% of days relative to the average day at each particular grid point in one climate model, GFDL CM4, under the SSP 245 global warming scenario. So these temperature changes are anomalies between the end of this century following the SSP 245 scenario relative to the historical simulation. And everywhere where you see red or orange or brown indicates that the ratio of the warming of the hottest 5% of days to the ratio of the average warming at that grid point is greater than 100%. So you're seeing enhanced warming of the hottest 5% relative to the average day across really most of the tropics. And particularly if we average over land and ocean in the tropics, this enhanced warming of hot days becomes more apparent. So here I'm showing on the y-axis the temperature change averaged over the tropics, in red for red over all land regions in the tropics, and in blue averaged over all ocean regions. And I've plotted the temperature change as a function of days exceeding a given temperature percentile x on the x-axis. So there's going to be quite a few of these figures for the rest of the talk. So the way to read them is that on the right hand side you're looking at the warming of the hottest, in this I've indicated the warming of the hottest 5% of days. So this is the average warming for days exceeding the 95th percentile of land temperature. Whereas on the left hand side you're looking at the warming averaged over most of the days. So I've also indicated the warming of the 95% of the hottest days, which is at the fifth, which is at percentile 5 on the x-axis. So that's how to read these figures. It's the warming or another quantity averaged over days exceeding the given percentile on the x-axis. Okay, so that's how you read the figures. But what does this figure actually show? And just to note that now I'm showing the mean of 18 different CMIP6 models between the SSP 245 simulation relative to the historical simulation. And we see two key features. The first key feature that we see is that we have this well-known land-ocean warming contrast, whereby for every percentile, the land tends to warm substantially more than the ocean. But what I'm particularly interested in today is the amplified warming of hot days relative to the average day. And this is particularly true over land. So as we move towards the right in this figure, for hotter and hotter days, the warming of those hotter days is larger than the warming of the average day, which would be the value at the left-hand most side of this figure. So we're seeing this red line tilting upwards as you go to higher and higher percentiles, which is indicating that these hot days are warming more than the average day. Okay, so this is the multi-model mean, and here I'm showing the interquartile range across models at each percentile, and we see that there's quite a bit of spread across models in how these hot days will warm in the future. And this is important because many of the negative implications of climate change are associated with changes in extreme temperatures. So amplified warming of extreme temperatures is bad news for human health, animal health, wildfire risk, food production, and many other aspects of life in tropical regions. Okay, so these are the temperature changes. You can also express this amplified warming in terms of a scaling factor, which I've defined here as a change in temperatures exceeding a given temperature percentile x divided by the average warming over all days. And what we see, again, particularly over land, is that the higher the temperature percentile, the more those days warm relative to the mean. So if we look at the hottest days over land, so if we look above, say, the 90 or 95th percentiles, those days are projected to warm by more than 20% more than the average day. And this, as I mentioned, there are main negative implications of this enhanced warming of extreme days relative to the average day. So the question I want to address in this talk is, why is warming amplified for hot days over tropical land? What's the mechanism? So I'm going to introduce a theory to explain this amplified warming of hot days. And the theory has two underlying assumptions. The first is that there's active convection in the tropical atmosphere. And the second assumption is that temperature gradients are weak in the free troposphere in the tropics. So going into each of these assumptions in a bit more detail, the first assumption follows from the idea of convective quasi-equilibrium, which some of you will be familiar with. And the basic idea is that in the tropics, you have active convection, meaning that you have frequent mixing of air and a quantity called moist static energy by convection. So convection acts to mix moist static energy up and down in the vertical and tends to homogenize moist static energy in the vertical direction. And note that moist static energy is an important quantity in tropical atmospheric dynamics because it's conserved under moist adiabatic processes. Okay, so that's the first assumption, that we have convection that's happening quite frequently in the tropics and mixing this moist static energy up and down. The second assumption underlying the theory that I'm going to develop over the remainder of the talk is that we have weak temperature gradients in the tropical free troposphere. And this idea has been around in tropical dynamics for quite a while. And the idea is that because the effect of Earth's rotation is weak close to the equator, above the boundary layer, there's no force to balance a horizontal gradient in temperature and an associated gradient in pressure. So this means that gravity waves act to very efficiently dampen out any gradients in temperature in the tropical free troposphere, such that the temperature in the tropical free troposphere is roughly spatially uniform. So when you put these two assumptions together, the first being active convection in the tropics and the second being weak temperature gradients, what these two assumptions together amount to is they amount to assuming that near surface moist static energy, which is a function of temperature and specific humidity, that changes in this near surface moist static energy are approximately uniform across the tropics and therefore equal over land and ocean. And this is really the important constraint that we're going to use to develop this theory for the warming of hot days over tropical land, to explain this amplified warming of those hot days. So active convection and weak temperature gradients imply that changes in moist static energy near the surface are approximately equal over land and ocean. So that's what these assumptions imply. We can check this in our simulations. So here I'm going to plot changes in land quantities divided by changes in ocean quantities. So then any value above 1 indicates enhanced warming over land, an enhanced change over land relative to the ocean, whereas any number below 1 indicates stronger changes over ocean compared to land. So if we look at temperature first, at the full range of percentiles, we see that changes in land temperature are greater than changes in ocean temperature for every percentile. So this ratio is above 1 for all percentiles. And we're familiar with this idea that land temperatures tend to increase more strongly than ocean temperatures. If we look at changes in specific humidity, so the amount of moisture in the air over land and ocean, what do simulations suggest will happen to specific humidity in a warming climate in the tropics? They suggest stronger increases in specific humidity over ocean than over land. So this ratio is less than 1, particularly for percentiles of specific humidity below about the 50th percentile. So this makes sense. This suggests that you have bigger increases in moisture in the air just above the ocean than you do in the air just above the land. But now if we look at changes in near surface moist static energy, which is a combination, remember, of temperature and specific humidity, we see that above about the 50th percentile of moist static energy, changes in moist static energy over land and ocean are approximately equal. So this provides support from simulations of our assumption of roughly uniform changes in moist static energy across the tropics. So now I'm going to use this idea of uniform changes in moist static energy to explain the amplified warming of hot days relative to the average day. Okay, and first I'm going to do this in an intuitive way, and hopefully a way that you can find fairly digestible and fairly easy to understand before going on in the next part of this talk to develop the full quantitative theory based on this constraint. So if you want to just watch the first part of the talk, you can do that, and you can take away from this talk the key take-home message basically at this point. And the key message is that warming is amplified for hot days over land because those days are dry. So how can we understand this key take-home message? So let's consider on the left a dry day, or you can consider a dry region in the tropics, and on the right a wet day or a wet region in the tropics. So the dry days, the change in the moist static energy on dry days is just equal to delta H dry, which is equal to Cp, which is the specific heat capacity of air at constant pressure, times the change in temperature on those dry days, plus Lv, which is the latent heat of vaporization of water, times the change in Q dry, so the change in specific humidity on those dry days. And similarly, we have the change in moist static energy on wet days or in wet regions on the right. So under climate change, moist static energy goes up everywhere because you have warmer temperatures and you tend to have increases in specific humidity. So let's consider the increase in moist static energy on those wet days or in the wet regions. So we have some increase in moist static energy H, which is some combination of an increase in temperature and an increase in specific humidity. Okay. Now, what about on the dry days or in dry regions? Now, because of the two constraints in the tropical atmosphere, which we mentioned earlier, so active convection, which tends to mix moist static energy in the vertical, and weak temperature gradients, which tends to flatten out temperature gradients in the free troposphere, the change in moist static energy on dry days is approximately equal to the change in moist static energy on wet days, or in wet and dry regions. But because dry regions and dry days are dry, the increase in specific humidity for those days under climate change is constrained because on dry days you have a dry land surface, you don't have much moisture to evaporate. So the increase in Q, specific humidity, on dry days is limited by moisture availability. So in order to have the same increase in moist static energy in dry and wet regions, the increase in temperature in dry regions must be amplified to compensate for the small increase in specific humidity because those days are dry. And this is essentially the reason why hot days over land, which tend to be drier, are warming faster than the average day. It's because those days are dry and you need a bigger increase in temperature to compensate for the limited increase in specific humidity associated with those days being dry and arid. So that's the take-home message, and I'm going to, this is the end of part 1 of this talk, and in part 2 I'm going to go through in detail the development of the quantitative theory to show exactly why you get this amplified warming of hot days relative to the average day. So thanks very much, and I hope to see you in part 2.